welcome back. So if you've been following along so far, you will have seen in the last video that we talked about how photons interact with matter. It was sort of a theoretical calculation at the microscopic level, right? And now I want to take that more to the macro level and see about something that we can observe in the clinic. So we're going to talk about beams, X-ray beams, both therapy and diagnostic, and how those beams can be quantified in ways that you can measure, and kind of like relating it back to those basic principles that we just learned in the last video. All right, here we go. So we're going to start with this picture of mass absorption coefficient and turn it into something that you can actually use to do a calculation. And so I will write some equations that describe that process. So first of all, consider that you have some small slab of material and it's going to have some width delta x. And then consider some photons going in and some photons going out, and you lose some number of photons n, delta n. You start with some number of photons n. So the number of photons that you lose is going to be proportional, and I'm going to write the proportionality constant as some minus mu. It's going to be proportional to how thick the material is, right? The thicker it is, the more photons you're going to lose. And it's going to be proportional to how many you started with. You know, if you start with 10 to the 6 photons, you're going to lose many more photons than if you start with just 10 photons, right? So it's got to be proportional to the number. So I write this with calculus notation, the n dx, and that's equal to minus mu n. And then you'll recognize this equation. It's the same as what we saw in brachytherapy and decay calculations. And so you'll recognize immediately that the solution to this equation is n equals some initial n0 times e to the minus mu x. Okay, it's just exponential absorption, so it's very simple. And then just like in brachytherapy, we don't usually talk about the absolute number of photons, we talk about the rate. So it's actually the rate you could write as the intensity, number of photons per unit time. It's equal to the initial intensity that comes in, and then it's attenuated by this factor. So this mu value is called the linear attenuation coefficient. And it has units of 1 over centimeters. And you can look it up. Now, we don't usually talk about the linear attenuation coefficient. We want something that's intrinsic, that doesn't depend on how much material you actually have present. So we actually usually talk about this value, mu over rho, and that's actually called the mass attenuation coefficient. Now the units of mu over rho are just, you can work that out, it's just 1 over centimeters for mu, and then rho would be grams per centimeter cubed. So in these units, the value is centimeters squared per gram. And so if you look up mu over rho, you can immediately get mu, because mu is just the value that you look up, the mass attenuation coefficient, times the density of the material. And then once you know mu, you could calculate the attenuation according to this formula. So we can derive some interesting properties now right away. You'll notice that the form of this equation actually looks a lot like an equation that you've already seen for the activity of a source with nuclear decay. And so a lot of the math is actually going to be the same. And so we can do, first of all, just like we derived what the half-life is, we can derive something called a half-value layer, and that's the thickness where the intensity is half of the initial intensity. And so the equation becomes this. And if you solve the math and do the logarithm and everything, you'll see that the half-value layer, which we call HVL, half-value layer, is equal to the natural log of 2, 0.693, which of course you have memorized now, 0.693 divided by mu, the linear attenuation coefficient, in exactly the same way that the half-life here was equal to that same number divided by the decay constant. The math is the same. I'm not going to derive it again. With the same kind of logic, you can show that the intensity after some number of half-value layers is just 1/2 to that power. So that 1/2 to the number of HVLs. So if you have 1 half-value layer, it's 1/2, or 2, it's 1/4, and so on. That's completely similar to the activity. And then within attenuation, we often talk about, instead of half-value layer, a 10th value layer. And that's because it's just a practical for shielding calculations. So 10th value layer, TVL, and it's the same logic. The intensity is 1/10 to that power, to the number of 10th value layers. So these are the equations. Now, it's important to remember that when we're talking about all of this, we're actually talking about an idealized situation, where it's the attenuation of basically a monochromatic beam, one beam of one energy. And there's no scatter, and there's the spectrum of the beam doesn't change. And that's not really an actual therapy or diagnostic beam. This is an idealized situation for sort of educational purposes. But if you were to go and measure it, you'd have to measure it in a very small beam, narrow beam, where there's no scatter, or the scatter is minimized. And people actually do that in order to measure the half-value layer. Okay, so now we understand the math a little better. I can go back and just talk for a little bit about one thing I wanted to mention about the attenuation coefficients and how they depend on materials. And this is particularly important for therapy. All right, so to understand this next part of the video, we're going to have to understand the process of photons interacting with electrons in the atom, and in particular how it depends on the Z, atomic mass. Now let's consider Compton scattering here. So that Compton scattering, you remember, an electron gets kicked out of the atom, and then it goes on and deposits dose in tissue. So what is the Z dependence for the probability of a Compton interaction? Well, let's look at this table to understand that. So this table is showing several different common materials and the atomic number or effective atomic number of each of those. And then on the right, you'll see the number of electrons per unit gram in the material. Now, that's an important quantity because the amount of Compton scattering you get is essentially going to scale with the number of electrons per unit gram. You have more electrons, you have more Compton scattering, right? So you'll see here that most of these materials have approximately the same number of electrons per unit gram. And that means that the amount of Compton scattering is going to be approximately the same in these materials. So that's the first basic learning point. But there are deviations from that and exceptions. So a big one is hydrogen. So you'll see that has a large number of electrons per unit gram. And that is because there's no neutron in the hydrogen atom. If there were a neutron, you'd have a heavy mass in there with no electrons that went along with it. But there isn't a neutron, and so there's more electrons per unit gram. So hydrogen-rich compounds are going to have more Compton scattering. And then on the other end, you have these high Z materials. And the example shown here is lead. They have slightly fewer electrons per unit gram. And that's because these high Z elements, as you recall, tend to be more neutron-rich, which means they will end up having fewer electrons per unit gram. So these patterns are going to explain the Z dependence of Compton scattering. So let's look at how this plays out on this plot of mass absorption coefficient versus energy. Up here is the Compton regime, and you'll see that it's roughly independent of the Z of the material. Right? This mass absorption coefficient doesn't really depend much. Okay, when you go to really high Z materials, it can. And then down here, of course, this is the photoelectric regime. Of course, it does depend a lot on the Z of the material. Okay, so now we can understand what happens to a beam as it passes through material. So let's start by looking at an energy spectrum. And let's say this is a diagnostic spectrum and the highest energy is up here, a little bit above 100 keV, and then it peaks at low energy and comes down. This might be from an X-ray tube. Now, if you send this type of a spectrum through a material, it's going to differentially attenuate. So let's just pretend it's going through some layers of lead. Okay, and here's what the attenuation coefficient looks like for lead. And so it's going to attenuate the beam more down here at the low energy than it does up here at the high energy. And so after the beam passes through some thickness of lead, it's going to be more attenuated down here. This is going to rise up, and then, as it gets to higher energy, less and less of the beam is attenuated. And so if you look, this actually changes the quality of the spectrum. If I were to calculate what the mean energy is of these photons, for the red curve as it enters, it would be somewhere here, let's say. And then for the spectrum as it exits, the mean energy might be, let's say, up here. And so you'll actually see that the mean energy is increasing. And this is referred to as beam hardening. Hardening means that the energy, mean energy, goes up. That's an important concept. It's true of really of any material that the photons pass through. Okay, so another way this beam hardening manifests is actually a change in the half-value layer as the beam penetrates. And you can visualize this in this way. If the beam starts up here at some initial intensity, and this is a log linear plot, so it would drop here to, let's say, half the intensity in some thickness that's equal to 1 half-value layer. Okay, and if the beam were to keep attenuating that way, with standard attenuation, you would see this type of a plot extending down to in log scale, but it doesn't. What happens is the beam hardens. So now as it goes down to the next half-value layer, where you're going to get down here now to a quarter of the beam, it's not going to follow that line. It's actually going to take longer for it to get there. And I'm exaggerating this, but let's say it goes like this. Okay, and then the next half-value layer is going to be even longer, and so on. So it's going to kind of even out like this. So the idea here is that it's actually hardening as it goes down. The energy is getting higher, and so as you go through more material, the beam is harder. It takes longer to attenuate, because remember the half-value layer is equal to some number over the linear attenuation coefficient. And so as this value gets smaller, this value gets larger, and eventually it kind of asymptotes. Good. So with that, you understand the basics of how you can quantify a beam in terms of its energy and its attenuation and so on. And so in the next video, we're going to now see then how you translate that into actually a dose inside of a patient, which is what you really need to know. I'm going to leave you with a little bit of further reading that you can dig into this deeper. And then I will see you in the next video. Thank you.